I found this paper about doing mobile video object detection. Basically, because it's run on a mobile phone, it has to be very efficient, and because the resources are very, very limited. First, here are the things that we are going to be talking about: the introduction and the biological inspiration, the historical techniques, the model architecture itself, the model results, and then some concluding remarks. One of the things that the author was fascinated by is that the human eye fixes on a single point for a fraction of a second, and the eye is basically moving in a saccade from place to place. But the eye manages to generate a very rich representation of the entire stream. And basically, using prior memory, you can very quickly detect objects in a very efficient manner. So using this inspiration, the author constructed a model which can run real time on a phone on a video. So what it does is it keeps memory of prior frames to decrease the computational cost. And it uses two feature extractors, one that's slow and accurate, and one that is less accurate but very, very fast. And it relies on the memory to maintain the accuracy level. So some historical techniques. The first one is basically a temporal CNN, which propagates the detections from one frame to another. This is not very different from making a detection on a single frame or a single image. And the detections are then linked together to form tracks. The next evolution was optical flow, and I think Sheraz covered some of this. So the optical flow propagates features in a CNN across frames. So in a sparse optical flow, it will take some key points, as you can see in the GIF below, and it will propagate them from one frame to the next. It's faster than a temporal CNN, but requires optical flow data and also a pre-training stage. This particular model that the paper mentions, here are some definitions. I think most of this has been covered, but the main one that this paper relies on is the LSTM, the long short-term memory. That module basically serves as the memory node. So that is very, very important for this particular paper. The other definitions and acronyms are covered, but not in as much detail. The model highlights this model is not dependent on optical flow. It combines the context from previous frames and the gist from the current frame to do object detection. It uses the memory-guided approach where it interleaves a number of different features extractors. And it uses an adaptive policy to decide which feature extractor to run, like whether it should run the slow accurate one or it should run the fast one that isn't as accurate. This is a representation of the model interleaved. The F0 model is based on MobileNet v2 with parameters that are optimized for accuracy. And the F1 model is also based on MobileNet v2, but it's optimized, the parameters are optimized for speed. So the accuracy level for the small feature extractor is actually about 0.3 versus the large one gets around 0.6 for reference. The memory-guided interleaving has a number of advantages. Multiple feature extractors can be run sequentially or concurrently. A large number of feature extractors can be specialized for particular areas of expertise, and then they can be combined to create a temporal ensembling effect because each of them are doing something slightly different. Frame level feature extractors can be augmented using the common memory module, which is represented in green in this diagram. This is the architecture of the memory module. It's basically a modified LSTM. The memory module basically aggregates and augments features, especially from the smaller model, which doesn't have the accuracy on its own. And it combines features from different extractors in addition to propagating the features from one frame to the next. One of the weaknesses of the LSTM is that it can't completely preserve its state and there is loss over time. The solution this model comes up with is it basically skips the LSTM state update and always uses the output state from the large model, the last large model that was run. So there are two types of interleaving. Fixed interleaving basically is very simple, where the large model is run every t frames. Adaptive interleaving relies on how much accuracy the current object detection has. And if the accuracy drops below a certain threshold, then it's going to run the large model. Otherwise, it will just keep running the small model. They came up with a reinforcement learning model, which controls the adaptive interleaving. So the memory module contains a measure of how accurate the detection confidence is. And the reinforcement learning policy network examines this, the memory module, and decides whether to run the large model or the small model. The reinforcement learning reward system is based on two parts: the speed reward, which is given every time the small model is run, and you can vary the mix, and the accuracy reward, which is based on the detection loss, like how accurate the detection is. The result is that the large model is only run when needed to maintain accuracy. So here's a graphical representation of this. In the top row, you can see that the deers are fairly well recognized. The detection confidence is not dropping. Therefore, the red frame is the one where the large models run. So it's only run once, and then the small model is continuing the accuracy. The last row, the airplanes flying through the air have very low object confidence. So the large model is running every frame. And you can see results in between in the middle rows. Another thing that this model allows is asynchronous running of the different feature extractors. So the small model doesn't have to wait for the large model to finish running. If that was the case, then there'd be a huge lag between the frames that the large model was running. So the small model basically runs concurrently with the large model. And once the large model is completed, the small model will use the output state of the last completed large model, which means that there's no lag when the large model is run on a particular frame in between frames. So the model results. This model achieved, so that's the last row where they have interleaving, quantization, adaptive, and async all running at the same time. They achieved 72 frames per second on a Pixel 3 mobile phone while maintaining the same accuracy as some of the best single frame detection models. MAP in this case is basically very similar to area under the curve, but for object detection. And MAC is very similar to floating point operations. So how many operations were needed to do the calculations. So this, the MAC basically gives you a representation of how heavy the model was, and the MAP gives you a representation of how accurate the detection was. So you can see that this model has fairly good detection, but at a very, like at a much lower computational threshold. Conclusion is that this model is competitive in accuracy with the best models while being extremely fast and lightweight. It does not rely on optical flow. It interleaves small and large feature extractors using a memory module. The memory module allows the small model to be run without losing accuracy. The reinforcement learning adaptive policy runs the large model only when needed. And asynchronous processing prevents the small model for waiting for the large model to complete. With that, thank you. And here is the original paper. Any questions?
Can you go back to the results table?
Yes.
So interleave is the most basic stuff they use, right?
Yes.
So the non-interleave would be, so the FPS for the large model is 4 and the smaller model is 48.8. Is that the correct way of reading it? I'm looking at non-interleave
Yep.
one. So if I use just a large model, it's 4. If I just use a small model, it's 48.
Yeah, so when...
Oh, that's interesting. So that means with the async, it is going as fast as a small model?
So yeah, like it's interesting. Like so quantization, I really didn't understand. That was basically the architecture of the LSTM. They
Oh, that
were
one is,
they
I'm
were
guessing
quanti
they're probably quantizing the weights or the outputs or something like that.
Exactly, and that like from like my little notes I scribbled here, quantization led to like 16 extra frames per second, and asynchronous actually had the biggest jump, which led to 30 extra frames per second. So in terms of importance, I think the async is extremely important, followed by the quantization, and the adaptive in this case didn't seem to have much of an effect at all. Even
What is the difference between adaptive and async again? I know
so
async you run both models at the same
Yeah,
time, right?
async is where the small feature extractor doesn't have to wait for the large feature extractor. So the feature extractors can run concurrently rather than sequentially. Adaptive is where it decides which feature extractor to run based on the confidence of the object detection. So if the confidence of object detection is low, it runs the large accurate feature extractor. If the confidence is high, it keeps running the small extractor and it gets like a
Oh,
speed reward for it.
okay.
So,
That means with that adaptive is just the one where it just waits for it to catch up and then it just uses
So
it.
without adaptive, you would basically set it to, let's say, run every five frames. So every 5 frames run like the large one, or every 20 frames. Uh, they they made a big deal out of the adaptive, and they claimed that it had benefits, like at all thresholds that they
No.
set the adaptive at. But in these results, I don't see those benefits. In these results, I mainly see the benefits of the async and the quantization. But I covered adaptive in that much depth because they covered it like a third of their paper was about adaptive.
Okay. All right. Well, really cool stuff.
Thank you so much.